Welcome to part two of our discussion regarding minerals. We are still looking at some basic chemical principles or chemistry principles to allow us to look at minerals and get an appreciation for really what a mineral represents. And so in part one, the previous discussion, we looked at elements. We decided elements make minerals, minerals make rocks. We explored the structure of the atom by looking at the atomic number, the atomic mass, and understanding what it means to be electrically neutral. And in this part two, we're going to look at how atoms bond together, and we're going to look at the different types of bonds that produce various types of minerals and give some of the minerals their physical properties. So to start with, we're going to take an atom that you look at the middle portion of your screen, bottom middle portion of your screen. And this is an electron configuration where now we have the protons in the nucleus, but at this point, we're not going to be concerned with the protons. We're still going to maintain the atomic number of the protons or the atomic number of the atom, which will never change with respect to the atom. So the atomic number always stays the same. But in this case, for bonding atoms together, we are now going to play around, if you will, with exchanging electrons. So for example, in this diagram that I have shown you, these are the orbital shells that surround the nucleus of the protons. And in the first outer shell, to satisfy the energy capacity for that particular shell, the first shell from the nucleus always is occupied by 2 electrons. And then the next outer shell is typically occupied by 8 electrons, and then followed by the next orbital shell, which also occupies 8 electrons. So really, what the atom wants to do is it wants to be stable by always having 8 electrons in its most outer shell. So in this case, in this particular atom that you're looking at, again, we have 2, we have 8, and then at the very last orbital shell, we only have 1 electron. And so this is where then that atoms combine with one another. So all chemical reactions or atoms bond using the electrons found on the most outer shell of the atom, and this is known as the valence shell. So what we really want to say is that all chemical reactions take place along the most outer shell, the valence shell. And in this discussion, we're either going to allow the valence shell to take on electrons to satisfy that rule of 8, or we're going to allow electrons to transfer or move from the outer shell to satisfy that rule of 8. And once the atom has the rule of 8 satisfied, then that atom now becomes stable. So again, electrons enter higher shell levels after lower shell levels have been filled. So that would be the 2 on the first shell, 8 on the next shells. And then here, then electrons will either be shared or transferred to other orbital shells. And now in all reactions, again, always take place along the valence shell. And then here, then, once electrons either are shared or transferred, that changes the physical property of the atom itself. And so atoms then are going to either lose or they're either going to gain electrons. And when that happens, it now takes it from an elemental state in which the atom was electrically neutral and now changes the charge of that atom and creates a new chemical species that we know and call ions. So ions basically represent the net electrical charge of the atom. So in this case, we would say if the atom loses an electron, it becomes positively charged. If the atom gains an electron, it becomes negatively charged. Now, rather than memorize loses, positive, gains, negative, I would much rather have students understand why that is the case. So let's look and revisit our atom here. And as we indicated, the protons, the atomic number never changes. So in this particular case, this is an electrically neutral atom. And if it's an electrically neutral, that means electrons must be the same number as the protons. So we've counted 11 electrons on this particular atom, which means it has 11 protons. And again, the protons, the atomic number doesn't change. However, if we move up to the valence shell, and let's say in this particular situation, this electron is transferred or leaves the valence shell, that means that if we lose the electron, then this particular species becomes more positive, because now we have still have 11 protons, but 10 electrons. So that's when we say that it loses an electron, but it's more positive. And we would call that a positively charged ion. On the other hand, if this particular atom gained several electrons to satisfy that rule of 8, then in this case, it would now be more negative. And so we would say it gained an electron, and therefore now it's more negative and it's negatively charged. And so that's how we describe the meaning behind positively charged ions and negatively charged ions. And again, once the electron is either transferred or gained, now it's no longer an element, but now it is a charged particle, which lends itself to a whole host of different characteristics. A couple other terms I want to introduce is the term at the bottom of your slide, and that is when we are positively charged, this is known as a cation. So we use the term cation, and if it's negatively charged, we use the term anion. So we are now going to take the next several slides, and we're going to start adding and subtracting electrons along the valence shell to form different chemical compounds, or in this case, minerals. So an example then I'll show you is combining elements to make minerals. And elements are bonded through, again, I like to use this term electrical glue, using electrons from various element configurations, compounds. And so compounds will then display completely different properties. So we can take two elements, combine them together, and produce a compound that has completely different properties than what we started with. And that really is the essence or the definition of really what chemistry represents. So my example here is, let's take sodium. And sodium in its elemental state is very metallic. It's got a physical property where it's very soft. And as we explained in part 1, sodium is very explosive. And as in fact, if you were to eat sodium as an element, it becomes very lethal. You would not survive very long. And now we're going to add to that chlorine. And chlorine in its elemental state is a yellow gas, so it exists as a gas. And if you inhale elemental chlorine, it's very lethal. Again, you would not last very long. So here we have two lethal type elements when they're in their elemental state. And in chemistry, we're going to call these reactants. So you see where the sodium is added to the chlorine, and now it's reacting. And once it reacts and combines using the valence shells of each, the sodium and the chlorine, it produces a completely new product, or what we would refer to as a compound, a chemical compound, which we refer to as a mineral. And in this case, the mineral becomes halite. And halite is just basically normal table salt. And if you look at the description now, the properties have completely changed. So halite has new properties. It's a compound. We can eat it, and we need it. And so here is a very good example of, again, the essence of what chemistry is. Taking two complete substances with complete different properties, allowing them to react with one another along their valence shell, and producing a completely new product. In this case, our example, halite. And that's really what a mineral represents. And recall, we said elements make minerals. And so this is a classic example of that. So we're now going to look at then how the atoms bond together as elements, and we're going to look at 4 different types of bonds in which we're either going to have electrons transferred or shared or free moving or just attracted to each other. And in all cases, again, the chemical reaction will take place along the valence shell or the most outer shell of the atom. So we're going to look at ionic bonding, covalent bonding, metallic bonding, and van der Waals bonding. So in our first example is the ionic bond. And in the ionic bond, the electron is electrically transferred to the other atom along its valence shell. So what we're looking at then on the screen is the sodium atom, and you're looking at the chlorine atom. And now you're just looking at the configuration of electrons where it's just showing you the electron on the valence shell only. So in other words, we don't really care or need to look at the other shells because they have already been satisfied with the rule of 8. So you notice then on the sodium atom, it has 1 electron on its valence shell. And on the chlorine atom, it has 7 electrons on its valence shell. So nature needs to decide how is this going to combine to allow the rule of 8. Well, if we allow the rule of 8 to be satisfied so that we can produce a stable compound, the sodium ion is going to want to lose its electron because it's a lot more energy efficient to lose the electron instead of trying to find 7 other electrons. So in this case, the sodium is going to lose the electron, and this now becomes a positively charged ion. And then the chlorine is going to now want to gain that electron to satisfy its rule of 8. So the chlorine gains the electron, and now it becomes a negatively charged ion. And so this ionic bond union between sodium and chlorine then produces, and there it is right there. So you can see where the electron was transferred over to the chlorine. In fact, let's look at that again. And so we look at that again. There's our electrons. I worked really hard on this animation and moves the electron from the sodium over to the chlorine and now produces the compound sodium chloride. So again, this is a great example of an ionic bond. And in this case, the electron was electrically transferred from the sodium to the chlorine. So we would say an ionic bond is an electrical transfer of electrons. The ionic bond then, when it becomes a mineral, really represents a very moderate strength and hardness. So in many cases, if you're looking at a mineral that's been ionically bonded, you can take that mineral and often scratch it with your fingernail, scratch it with a knife blade, because basically you're breaking these little ionic bonds. And in some cases, the ionic bond can be a weak bond, especially with salt, because what happens when you put halite or salt in water, we find that it dissolves because the nature of the water molecule being a dipolar molecule basically interrupts that transferred electron and separates the sodium chloride into the sodium ion into the chlorine ion. An example for minerals with respect to an ionic bond, of course, would be halite, table salt, and another mineral that we'll see a little bit later called biotite. And the mineral biotite, actually, you can take that mineral and you can actually peel off little layers because you're breaking them along the ionic bond. So again, the ionic bond is an electrically transferred electron. So now let's take a look at the relationship of the ionic bond with the periodic table. And so as we discussed earlier in part 1, we know that the periodic table was divided up into metals, nonmetals, and metalloids. And if you look at your screen, you can see that I have boxed off all the metals. And typically, the metals will have a tendency to lose electrons at the valence shell and become positively charged ions. So let me repeat that. Metals will typically lose their electrons and become positively charged. And on the other hand, the non-metals will typically gain or share electrons, and it shares them at the valence shell, and they become negatively charged. So in the science of minerals and mineralogy, most minerals are a combination of metals and non-metals, where we lose and we gain electrons to satisfy the valence shell. Another term that I want to incorporate into this slide, and it's a term that was in the previous slide that I don't think I went over, and that is that when we lose electrons and we become positively charged ions, these are known as cations, C-A-T ions, cations. And when we gain or share electrons on the valence shell of non-metals, we call those anions. So really, in mineral chemistry, minerals are a combination of cations and anions. So cations are positive, anions are negative. So here we can also then look at how we can predict chemical combinations or various compounds in mineralogy, but just by using the periodic table. So for example, in our example, sodium chloride with halite, we see that sodium is in group 1, which means it has one electron in its valence shell. And in fact, because this whole group here is group 1 or alkali metals, we would say that every element in this group, so that'd be hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they all have one electron in its valence shell. And if we come over to the non-metal side, this particular group, which is known as group 17 or the halite group, they all have 7 electrons in their valence shell. So readily we can take an element from group 1 and we can predict that it would have no problem combining and creating a stable compound with group 17. So you basically could take potassium, and potassium will readily combine with chlorine, which makes another mineral known as sylvite. And sylvite has similar characteristics to halite, except halite probably tastes a little better on our food than you would like to look at a potassium chloride of sylvite. And so what's interesting about the periodic table is if group 1 contains one electron in its valence shell, and we move over to group 2, which is the alkali earth metals, how many electrons would be contained in group 2's valence shell? Yep, you got it, 2. And we look at the transition metals, that's a little bit different. And when we come to metallic bond, we'll kind of talk a little bit about that. So the periodic table is really, not only does it organize the elements by similar properties, but it also makes a great way to predict various chemical reactions just based on the electron in the valence shell. So now let's look at the covalent bond. And the covalent bond is represented by sharing electrons. So remember, the ionic bond was an electrical transfer to satisfy the rule of 8 and become stable. In this case, the covalent bond is sharing electrons and sharing the electrons to become stable. So let's look at a single carbon atom. And so again, we don't really care too much about the protons because they never change. So we're concerned with the electron configuration that shows the amount of electrons or number of electrons in the valence shell. So here, carbon has 4 electrons in its valence shell. And so the question is, how are we going to satisfy, or how does nature satisfy this carbon atom by sharing electrons? How many does it need to be stable along its valence shell? And of course, the answer is it needs 4 more to satisfy that rule of 8. So how are we going to do that? Well, nature is going to say, let's put on 4 more carbon atoms. And if we put 4 more carbon atoms, you can see that this carbon atom we started with is now satisfied. It is now sharing an additional 4 electrons, which is now making it have 8 electrons. It is now happy. So by looking at this picture then, let's go ahead and take literally billions of other carbon atoms, and let's start allowing them to bond and share with other carbons. And if you did that, you would create a three-dimensional image, and you can kind of envision this image coming out at you at the screen and going sideways and backwards and produce this three-dimensional image of shared carbon atoms. And you would probably end up with something that looks like this. And we would coin that as the perfect geometry. And a perfect geometry with carbon atoms creates the diamond. And so here you can see the lattice work and the crystalline structure of a typical diamond. And then below that would be, of course, a cut diamond. So typically, in a covalent bond represents the strongest type bond. In this case, most minerals will scratch glass. One of the tests that we do to detect if a mineral is covalently bonded is we actually scratch glass. So these covalent bonds are extremely hard to break. In fact, if your significant other decides to buy you a diamond ring and you just want to make sure that this person is up and up with a true diamond ring, one can take that ring and just scratch it right across the windshield of the car. And if it scratches, then there's hugs and kisses. If it doesn't scratch, then it's most likely not a true diamond because it's not truly covalently bonded. Before we look at the metallic bond, in fact, let me just go back to this slide here. This is the covalent bond. A couple of examples you can put in your notes for a covalently bonded mineral will certainly be diamond. Probably the most common mineral on the Earth's surface is quartz, and quartz is definitely covalently bonded. Quartz will also definitely scratch a windshield. So now let's take a look at the metallic bond. And I think for this particular slide, I'm going to kind of work the slide backwards. And let's talk about some physical characteristics that you're familiar with and that you know about metals. What do you know about metals? Well, generally speaking, most metals are heavy. I think we can all agree to that. Generally speaking, metals are good conductors of heat and electricity. We can certainly polish metals. And in other words, you can put various solutions on the metal and polish it up and get its brilliance back. And so we need to come up with a chemical bond that will encompass and describe all the characteristics that we know about a metal. Because remember, chemistry is a man-made subject that describes the behavior of material. So when we look at the metallic bond, we're looking at a type of bond in which the atoms are going to be packed very, very tightly and very close to one another. And this is a form of sharing. And the outermost electrons, and this would be the electrons on the metal in the valence shell, are very loose, if you will, and they're allowed to freely move from one atom to the next. So in my diagram, I'm showing you a series of tightly packed cations, and these cations are metal ions. And you can see that we have electrons that are freely moving from one cation to the next cation. And this freely moving electron then allows the characteristics or the properties described as a metal. So to kind of reiterate then, that freely moving electron can allow good conductors of heat and electricity. The tightly packed cations allow the metal to be very heavy. And again, most metals are heavy, as we indicated. Metals are typically very malleable, meaning that they can bend very easily. So certainly if you take a copper wire, and as you hold that copper wire, you can bend it very easily. And that's because you have this free moving or free floating, loosely held electron. And then again, we indicated that metals are easily polished. And really what that means is that when you polish something, I like to restore old cars. I have 2 cars that I'm working on currently. And I know that when I polish the bumper, for example, I can bring out the brilliance in the chrome. And basically what we are doing is stripping away a layer of electrons. And so to get that metal to have that high polish, we're again getting rid of a layer of electrons. And if that metal then is exposed to oxygen again and just sits out there, it'll start to tarnish, and you would probably see the brilliance of the metal go away. It do the same thing over again, strip away that layer of electrons. So below are some examples of metallic minerals. Here's galena, for example. That's a lead sulfide mineral. You can see the Pb, the lead, and then S being the sulfur, and that gives rise to a real heavy, dense type mineral that's very, very shiny. And then here is pyrite. Pyrite is a very common mineral ore. As you can see, it's 2 irons to 1 sulfur. And I think another term for pyrite, I think most people have heard this, and that is pyrite can be looked at as fool's gold, but there's quite a big difference physically between pyrite and gold. And then, of course, the last example of a metallic mineral, I'm giving you gold. So again, metallic bonding represents that tightly packed set of atoms with a freely moving electron. So we've had the ionic bond, which we have an electrical transfer of electrons producing stable compounds. We've had covalent bonding, where it produces compounds in which the electrons are shared to satisfy that rule of 8 and make the compound stable. And then we looked at the metallic bond, in which we have the free moving electron that basically moves from cation to cation, giving the characteristics of what we know about metals. So the last bond associated with minerals is the van der Waals bond. And the van der Waals bond represents a weak attraction between molecules that have a positive and negative end, because we know that positive and negative charges attract one another. So we're going to use the example of graphite to illustrate our van der Waals bond. And in here, I have a set of carbon atoms that have now been covalently bonded together. So you have these covalently bonded sheets, if you will, of carbon atoms. And we're going to allow these sheets now to bond together through a weak attraction of negative and positive, creating the van der Waals bond. And when we do that, so there's your covalent bonds and your van der Waals bonds. So basically the sheets then line themselves up according to the positive and negative ends, and then creates a physical property in graphite, which produces very weak bonds. So out of all 3 types of bonds, the van der Waals bond is very weak, very easily broken, and because of the van der Waals nature, the layers will have a tendency to slip past one another. And this is real typical of graphite. In fact, if you have a pencil, most pencils today do not have lead, but instead they have graphite. And as you draw with your pencil, the little graphite layers are slipping past one another, allowing you to write your name, for example, with the pencil. You can also take a trip down to the local hardware store and purchase graphite lubricant. And I think a lot of folks use graphite lubricant to put into locks because of the slippage of one layer past another layer. It's handy for lubricating locks and so forth. So the question is then, at the bottom of your screen, why do graphite and diamond display different physical properties, in this case in terms of hardness, but yet they're both composed of carbon? So again, both composed of carbon, yet diamond can scratch glass, and certainly graphite cannot. Well, the answer to that is that it takes various kinds of geologic conditions to rearrange the carbon atoms either into a van der Waals versus a covalent bond. So for example, if you take carbon and you subject carbon to extreme temperatures and pressures typically found deep within the earth, and these are temperatures and pressures that even humans can't duplicate. And so we take this carbon, we subject it to those pressures and temperatures that typically will rearrange the carbon atoms into the very hard covalent bond, which then produces the diamond. So when you have a diamond, that diamond did not form on the Earth's surface, but instead formed deep within the Earth, again, where pressures and temperatures are high.